Welcome to today's webinar. The topic today is masonry wall design in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, and so on. I will be the moderator today, and I will also answer your questions together with Frank. But my two colleagues can introduce themselves.
Hello to all. My name is Ulrich Lex. I'm responsible for quality management of RFEM in by Dlubal, and I'm responsible for development some add-ons like masonry. And today I will be your presenter of the webinar.
Hello, my name is Frank Vollstich. I'm responsible for quality management and product engineering in Dlubal company, and today I will answer your questions.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. I say something about how you can ask questions for the attendees who participate the first time. You can show that panel here with that arrow, and then you can enter your question here. If you don't get an answer during the webinar, because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, then I hand over the screen to Ulrich.
So, hello again. Today's webinar is split in 3 parts. The first part I want to talk about is the material properties of masonry, especially what we need for an FEM analysis with RFEM. The second part I will take a look at it is to create a model or to compute a model with mainly vertical loaded masonry walls and using our isotropic material model. And the third part is what we want to do is to take a look on a shear wall, on an existing shear wall, where afterwards should be created some intersections, and we want to take a look if it can be done or not. So I will start with the first part, the material properties. The material properties of masonry are not so easy to find as for other materials. It's because the masonry is a mix between the bricks and the mortar. And so we have always to look what we have for product, and after then we can determine the characteristic strengths, for example, and to find the properties. So one of the basic characteristics what we need is the strengths. And if we take a look to the standards, Euro code 6, we find a formula. It's called Fk is K multiplied with Fb multiplied with Fm. This characteristic strength is a part of Fb is for the bricks, the part for Fm is a part for the mortar. K, alpha, beta are constants. When we now choose any product, then we can go to the website of a producer, and here you can find some data sheets where the producer gives some information about his products. If you choose now on Porotherm 38, for example, you can find an FB of 11.5 and a stone group of 2. With this information, we can go back to the standard and find that the constants k are 0.7 and the constant alpha 0.72. We had the FB, and with this information we can compute our characteristic strengths. In case of when we use a thin layered mortar, then does the part of the mortar have not an influence to the characteristic strengths. That's why we have only the part of K multiplied with FE. If we compute this, we get an FK of 3.87. When we go back to the data sheet, then we can sometimes also the value FK is given. And here you can see in case of thin layered mortar, we have an FK of 3.8. If we have another mortar, or here it's called dry fix, you have another FK. So the next step, what we need is the design value. The design value is only dependent from the characteristic strengths and the safety factor. And when you take a look to the standard, in our case we have a safety factor of 2, then you get the design value. So two another values we need, and it's on the one thing the Young's modules. The Young's module of the masonry wall is only dependent from the FK, and you find the formula FK multiplied with 1000. Here it's the left part is some reduction for the case of very small stones. If you have more very small stones, you have more mortar in the high of a wall, and this has an effect that the Young's module is lower. That's why we have here a reference high and needs a stone high. If you have the reference high, or if you have a stone high of about 250 millimeters, this factor is nearly 1. It has only an effect when you have small stones. In our case, we get now an Young's module of 3850, and the shear module is depending from the Young's module. It's with multiplied with 0.4, and you get a shear module of 1540. So far so good. Here I want to change switch to the program and want to show you how you can find these values in our program. So I create a new file. I activate our masonry add-on. And can create the new material. So I have to choose the material type masonry, use our orthotropic material model and can search in the database for our product. It was the Poroterm 38 thin layered mortar, and choose this product. So you have here the different cases, and you can see here automatically filled out the tables. You can find the group 2. You can find the mortar, thin layered mortar. You have the dimensions of the stone, and you can find this normalized compressive strength. If you go to the used parameters in the material model, then we can see that we have the ultimate compressive strength now in the loaded direction, the 1.93. When I go back to our presentation, we have a design value 1.93 computed. So it's exactly the same what we use in our program, what we now computed. The same is for the Young's module. We have an Young's module of 3,850 and a shear module of 1,540. A short check, 3,850 and 1,540. So if I change now our safety factor to 1, then you can see that it does not have an influence to the Young's module, but our compressive strength is according the safety factor 1. And that's all what we do. We use only the parameters from the standard for the calculation. So I want to continue in the presentation. So this computation, what we did is according to Eurocode 6. If we take a look on the national annex of Germany, then these formulas are a little bit different. In the national annex of Germany, there is used not an FB. For the stone parameters, it is used the FST instead. The FST is the medium stone pressure resistance. So you have to be a little bit careful because there are the same constant called, but they are a little bit different to the main document of Eurocode. But it is the same. You can choose any product from a manufacturer. You will find here an compressive strength class, maybe of 6, for the product of Poroton T8. And when we take a look on the standard, you will find that for the compressive strength class of 6, you have an FST of 7.5. The constants K and alpha are with 0.7 and 0.605, and you get the FK of 2.37. we can switch back to the data sheet, and here you can find also the characteristic fk of 2.3. So mostly you find this fk in the data sheet, but sometimes not. Then you can compute it with these formulas. The same is here for the design value. You have fk divided to the safety factor. In the case of Dean, you have 1.5 and get an FD of 1.58. The same is it for the Young's module. We have also again the formula fk with a constant. The constant is in this case 100, and the shear module is the same like before. Okay, this is all for the theory, and with these computed values we can continue with the second example. In the second example, I want to show you our isotropic plastic material model, where you can determine internal forces of a masonry wall. There is no design check done. It's only to determine internal forces. So for this, I prepared already an example where I have some concrete walls and concrete slabs, and here I want to add our masonry parts. Firstly, I will show if my masonry add-on is checked on. It's checked on, okay. So I can create a new material with our masonry. Now I want to use the isotropic material model, and I want to use our computed values before. Maybe we have the E module of 2600. I had to insert it here, 2600. And I had to add the shear module, 1040. Here I can add the specific weight. You can find it also on the data sheet. And that's all we need for this material model. One thing more what you had to enter is the limit stress of tension. Masonry does not have really a stress for tension, because if when tension is in the walls, then you get cracks and there is no tension resistance. So we have here to insert a small value. 0 is it's not possible or not good for the computation. So we have here to add any small value. At the end, I will show you what this tension have effects for the computation. If we have done all these inputs, we can continue with OK, and we can create our masonry walls. Oh, firstly, I have to create a new thickness where I use our masonry material type. This stone has a dimension of 365. Okay. And then I can create my surface. In this example, I only want to use these 6 surfaces of masonry. Okay, the loading I have already created. There is 1 times the self weight, the permanent weight, and the imposed load. And now we can check the FE mesh before the calculation. The FE mesh in general is 0.5. For masonry, it's more better to use 0.2 or 0.25. So I will create a mesh refinement. And assign it to my masonry walls. Okay, so far so good. That's all. And now we can compute the building. So, for the documentation of the results, I have already created one printout report, but here are only tables. And now I want to show you how you can document, especially the results for the masonry, to do any design checks with maybe an Excel file or something else. One good tool what we can use is the result beam. The result beam, when we create a new result beam, then you have the possibility to integrate stresses and forces from a surface and show these results as beam results. I use now the type to integrate with a block, maybe from 1 meter. Then I get the results per meter. I want to integrate the results of this surface. Okay. And create here a new result beam. The result beam itself has also a section, but it does not have an influence for us now. The only thing is the dimension of the integration, and this is 1 meter. We can here create a second beam. Okay. And we have here to integrate the results of this surface. Now we have to compute again. If you know that you want here create an result beam, then you can do before the first calculation. And now you can see that we do not have only the result, the surface results. We have the results of a beam to show it to you. And here you have also member results. The internal forces, the normal force, or also the moment. And with these results, you can do further checks. These results you can also document to the printout report. When you print it to the report, you can use the print graphic to the report. Here you have different settings, maybe as a screen, as window filling. You can define any scale or something else. If you say save and show, then the printout report is open and you can see where the picture is printed. You have at the end now the report, you get this picture of the results. A second possibility to document is to use the result diagrams. I want to show it on this wall. Here we can expect that the forces on the end or in the beginning are higher than in the middle of the wall. And this you can show very easily with the result diagrams. I want to show it for the surface number 18 on line number 108. Right click on result diagrams. Can here choose the surface number 18 on line number 108. And here maybe I can take a look on the basic internal forces, the Ny. It's our normal force. And we can see that the forces on the beginning and on the end are very high. Here you have the possibility to smooth the results. Maybe in a range of 25 centimeters. You can add a smooth area, and also for the end. On the end, it's maybe 3.25. To the end. You want to use it for the NY, and then you get real forces. You get maybe for the start, the nearly 90 kilonewton. For the middle term, you get 124 kilonewton per meter, and on the end you have 75 kilonewton. This picture can also print it to the printout report. You have to use again the print icon, print to printout report. You have the possibility to rotate the results. And when we again save and show, the printout report is open and the results are documented. So, and in this way you can take a look on each surface and print these pictures to the printout report to have all results what you need. Okay. That's all for this example. One thing I want to show you is the effect of the tensile strength. I have created one example, one wall with the material model isotropic masonry plastic. And if you now allow a very high limit stress for tension, then you can create the effect that the nearly point load is smoothing to the complete wall. So now you can see it on the angle. You can see that the small point load is above the whole masonry wall. If you now change the limit stress for the tensile to a very small value, then you can see that there is no smoothing of this load. You can see that the load is nearly directly goes through the wall and has no or not much smoothing. I choose now a tensile strength of 0.02. Because then I have a smoothing about the 60-degree, what the masonry normally have. So we can see that the smoothing is about the 60 degrees, and there is the load is smoothed. Okay, that was all for the second example. I want to go back to the presentation, and I will start with the third example, the shear wall. For the third example, we want to take a look on an existing wall, where I have an existing calculation, a wall with an vertical load of 390 kilonewton and a horizontal load of 80 kilonewton. The wall is 3 meters. The length of the wall is 3 meters. The height of the wall is 3.50 meters. And now I want to show, or I want to look if there can be created an intersection. I want to create I want to take a look on two different cases. On the first time, if we create the intersection in the lower part of the wall, and the second case when we create the intersection like a window, and we want to show if it's possible to create it, if the wall is then overloaded or not. So I switch back to the program. So for this case, or for this wall, it's the first time I want to create new material. With the orthotropic masonry material model, I want to choose one Prototerm 25. Okay. So I have to create a thickness with the Prototerm 250 millimeters. Okay. And can create now my shear wall. With dimension of 3 to 350 meters. The support downside is in Z, X, Y direction and around X. On the top of the wall, I only want to support it in Y direction. And here a small spring constant. So the horizontal load, I will bring up it not only in one point. So I want to create here. I want to divide the line. Okay. Here on the top of the wall, I want to add a small beam so that my horizontal load does not destroy my first FE elements. So I want to add here a small beam. And add here maybe steel, a small beam, 50 millimeters. So the last part, I had to create the load. One times the vertical load and the horizontal load. In vertical direction, I have 130. And 3 meters is my 390 kilonewtons, and 100 in X direction. So before the calculation, we have to take a look on the FE mesh. We want to use 0.25 millimeters. Okay, and apply. And then we can compute we can create one load combination. We want to use the large deformation analysis and set here some load increments. What is important for the plastic calculation? We can save the results if we want to take a look on it and have to assign both loads. Okay, now we can start the calculation, and now we can see the calculation is possible. The load is not, or the wall is not overloaded. What we would expect, because we have an existing calculation, everything is okay. So now I can what can I do? I can take a look how much horizontal load the wall can have before a damage, before it's overloaded. It's very easy. It's very easy to take a look at it, and I will do it now. So we have to activate our add-on stability analysis. And with this stability analysis, I can create firstly I can copy my horizontal load. Just again. Copy. Okay. I had. Okay, this now it's correct. So I can delete it. I can copy my horizontal load and reduce them maybe to a value of 10. Can create after this a new load combination. I have to use also for the load cases large deformation analysis and create now a combination of load case 1, my vertical load case 3, my reduced horizontal load, and can say, okay, my initial state is a vertical load, and I want to increase my horizontal load until the wall is damaged. Here I can also save the results to show what is to show the results in each load step, and I can use to activate some limit of deformation. Okay, with these settings, I can increase my load until the shear wall is overloaded. The calculation takes about 2 minutes. That's why I have prepared it with results and want to switch to this file. That's here. So when I take a look on the results, here the stability analysis was running, and it shows me that I can increase my load about 8 times, and I get a maximal horizontal load of 110 kilonewtons. If I want to take a look on the standard on the formulas to the standard, we can check it if it is the same. I have here a tool from Wienerberger where you can compute the maximal horizontal load. You can choose here your stone mortar combination. You can insert the wall dimensions. You can insert the vertical load, and you get a maximal resistance of shear resistance. And the formulas according to the standard leads to a value of 108 kilonewton, and we compute with our program a value of 110. So it's nearly the same. It's maybe I would say it's exactly the same, and it's good because that shows that our material model computes the same as the standard says. So now we can continue with our initial problem. We want to create an opening here in the lower part of the wall and want to show or want to look if the wall is overloaded or not. I prepared it already. I insert here an opening with the dimension of 40 centimeters in the height and 60 centimeters in the width, and want to take a look if I can, if it's possible to load an horizontal load of 80 kilonewton. There is the same behavior as before. I only create the opening and run the calculation. And the stability analysis, says that I can increase my load 8 times and get a resistance of 104 kilonewton. That says, or that the result is that we can create the opening. The wall is not overloaded, and it's possible. And you can with this program, can you show it in an easy way? When you create it according to standard, you have only the possibility to divide these two surfaces in two parts, and then I think it's not possible to create the opening. So the second case I want to take a look is to create, instead of the opening in the lower part, to create an opening like a window in the middle of the wall. I also prepared it. Now I created the opening like a window. Here it's needed to create a beam, a member above the opening, and I add also an hinge to avoid normal forces in the member. If you create it, you can use the same loads. You can do the same as before. You can start the calculation. You can run the calculation and see that the maximum horizontal load is now only around 50 kilonewton. So this is not possible to create such an opening, such a window in this existing wall, because then if you do this, then the wall is overloaded. But when it's needed to create an opening, then what could we do? Maybe we would have the possibility to create something like an frame inside of the wall, inside of the window. Maybe then it would be possible, and it is very easy to compute it. So I have the last example. Here I created not only the opening, I created additionally a something like a frame. Of course, the corners had to be welded. In my example, I used 2 HIR 140. I added also an hinge to avoid shear forces, because it's not really connected. So the masonry wall with the steel frame. And when we created this, we can again run our calculation and see that that the results with the frame are about 90 kilonewton maximum possible horizontal load. So you can also create this window in your shear wall. Okay, with this example, I want to show you what for possibilities you have. You can compute also on existing walls and find some solutions for problem what you have where the standards maybe give no solution. And with this example, I'm on the end of my presentation. I want to go back to the file. I want to say thank you for listening and go back to Andreas.
Okay, thank you, Uli, for your nice presentation. Before I will show where you can find the recording and models and so on, I would like to show my screen to give you a hint. If you want to get your free product demonstration, such as the showed module or add-on, or for another add-on, timber, steel design, and so on, just book your free appointment. You can contact our sales team with that link in the PowerPoint slide. You can download the PowerPoint slides. You can scan the QR code as you want. Also, when you would like to get a non-binding offer, just contact our colleagues. So then I turn to our website, dlubal.com. Under news and events, you can find the webinars. We record all our webinars. When you scroll down, where are past webinars that we presented in the past, you can search for webinars with the full text search. Those are the webinars that we will present in the future. That's today's webinar. I click on it. In the next days, I think after the weekend, you will get an email with a link directly to that page here. And then you will find the recording in the middle here. You already find the presentation slides here, and the models will you find here. They are already there because we present already a German webinar. Okay, just wait for the email with your attendee certificate and the link to that page here. That's also all from my side. Thank you for your attention. I hope we meet each other in a future webinar. Thanks to Ulrich Lex for the nice presentation. Thanks to Frank Faustich for the help by answering the questions. Bye-bye.